Hey, physics peeps. Today we're going to talk a little bit about gravity. So, the story goes that Newton, during the bubonic plague, he was at his castle hanging out, trying not to get the plague. And he's just sitting there, and all of a sudden, this apple falls onto his lap. When the apple falls and hits him in the head, he's looking up, and maybe the moon is setting on the horizon. And he starts thinking, well, if the Earth attracts the apple towards it, then who's to say that maybe the Earth isn't also attracting the moon towards it? Now, we don't know if that story is true or not, but it certainly gives us a good idea or a good framework of where maybe he came up with this idea of gravity. So he rationalized that if the Earth puts a force on the apple, then who's to say that the Earth doesn't also put a force on the moon? Now, what that problem with that was during that statement was at that time, they only really had an idea in Western European culture of contact forces. You literally had to be touching an object in order to make it move or to have a force acting on the object. So when Newton went to propose this, he was proposing a whole new type of force that was a non-contact force. Now, we now know that that's the case, and you probably have experience with a very easily known non-contact force like a magnet. I hold two magnets together, opposites attract, likes repel, and I don't have to be touching in order for those two things to be happening. But at that time, that was unheard of for them. And so Newton, who was very afraid of what his self-image would be like, he sat on this for almost 10 years. He came up with this idea of gravity. He could describe the force of gravity and calculate how it was, but he didn't know what actually caused that gravity. And he was so afraid of getting laughed at because of this contact, non-contact force that he didn't publish it. It wasn't until about 10 years later, he had a friend of his who said, hey, you know what? I have another guy who I know is working on this and getting ready to publish it. And if you want the credit for it, you need to publish or you're not going to get credit for it. So Newton rushed out, he published it. He was right. People laughed at him at first, but they started looking at Copernicus and Galileo's data that was leading into Newton's stuff. And they said, you know what? We really can't say you're wrong. This is right. We don't know what causes gravity to happen, but we can describe how it works. And it actually wasn't until about 10, 15 years ago that at the CERN Super Collider, we discovered the Higgs boson, and we attribute that that's what literally causes gravity. So imagine if Newton had to wait 300 years in order to publish this, someone else definitely would have gotten credit for that. So from the lab yesterday, you should have gotten these relationships where we said that the force of gravity has to decrease by the inverse square of the distance. So we have this F is proportional to 1 over r squared. It's an inverse square law. It happens again in electricity and magnetism, also happens in nuclear. It happens in all non-contact forces. Then we can also look at the masses and say, hey, because of Newton's third law, there's an equal and opposite force on the two masses. So both masses play a significant role. In the lab, we have this as M1, M2. You'll notice that I will often notate this as uppercase M, lowercase m, just two different masses. It doesn't matter which. It just helps to eliminate those subscripts. So as the big M gets bigger, then the force is going to get bigger because they're direct and linearly related. As the little m gets bigger, then the force is going to get bigger because they're direct and linearly related. So when we combine the two of those, we end up with this proportionality that is the force is proportional to mm over r squared. And this is what you graphed yesterday in your lab. So remember that to get rid of the proportional and turn it into an equality, we're going to add a constant. So we add this equals and some constant. Now, this constant value is the value that you had to find in your graph from the lab. Think through, doesn't this look very much like an equation that would be something like y equals mx plus b, where your g value is your slope, the y is the force, that mm over r squared is your x, and your b value, the y-intercept, should be 0, because if there are no masses, there's no force. If there's no radius, there's no force. And then that g value is the value that you got for your slope. So that value is 6.67 times 10 to the negative 11. Newton did not know that at the time. In fact, it wasn't until 100 years later that Henry Cavendish discovered the experiment for that, or created the experiment for it. And it's also considered one of the top 10 science experiments ever performed. I'll talk about that in a couple seconds. So this is just the word form of what this equation is. Every particle in the universe attracts every other particle with a force that is proportional to the product of their masses. That's the force in the two masses, and inversely proportional to the square of the distances. That's that F and 1 over r squared. And then this force acts on a line that joins both of those particles, okay? So that's the wording of what that equation means up there. Now, back to Henry Cavendish. So it took him 100 years later for this law to be proven. And the way that he proved it was he took and he suspended on a wire, had a pole hanging on the wire, and then put two heavy masses. One was actually a counterweight. So this one isn't important. The one on the left isn't important, other than it balances the pole. Now, this other one, try and picture it 3D. So if I have this one on the pole that's rotating or free to rotate this way, so maybe I have my pencil here, it's free to rotate this way, and I take another mass and I bolt it to the floor. Because there's a mass on this end and a mass on this end, then it's going to cause this one to want to spin towards that one. So picture, if I try and picture this three-dimensionally, if I bolt this one to the floor, it's going to cause this to want to rotate towards this mass. Now this one can't move because it's bolted to the floor. The trick then is figuring out, well, how much is that going to rotate? So if I take a really sharp beam of light, I shine it on a mirror up here, and I reflect it down onto a ruler. Boy, that's a terrible ruler. Down onto a ruler here, then as this rotates, won't it cause that beam of light to change where it's at on the ruler? And if I can't measure that because it's so small, then can't I move the ruler farther away? And the farther I get it, the bigger this distance becomes. So theoretically, as long as my light is really sharp, I can move that ruler further and further away until I get a good that I can measure that value. And that's what Henry Cavendish did 100 years later. Very, very cool. Very, very cool. So sample problem, a 50 kilogram boy and a 50 kilogram girl and a 70 kilogram boy are sitting on a park bench. So here they are sitting on a park bench. Here is the guy. Here is the girl. Terrible, not a cartoonist. And she says, I'm attracted to you. And he says, I love physics. Okay, so I'm attracted to you, I love physics. So I have a mass, I have a distance, and then I can do this F equals G m over r squared. So remember, this G value is a really, really small value, 6.67 times 10 to the negative 11. One mass is 50 in kilograms, the other mass is 70 in kilograms. And then for my radius, don't forget that we have to convert that into meters. So this is going to be 0.5 meters. The most common mistake students have on these problems is they forget to square that radius then. So if I take 6.67 times 10 to the negative 11 times 50 times 70 divided by 0.5 squared, then I'm going to get a value of 9.34 times 10 to the negative 7 newtons. So think through that. About all of the forces that we've studied so far, is 9.34 times 10 to the negative 7 newtons a big force, a small force, a medium force? And I would hope that you would say a really, really small force, because this times 10 to the negative 7 makes it really, really tiny. So yes, the two of them are attracted, but not very much. This times 10 to the negative 11 in the gravity constant makes the force of gravity a really, really small force. So I'm attracted to my computer. My computer and I are pulling on each other. But because our masses are so small, the computer doesn't move towards me. I don't move towards it. But I'm attracted to the Earth also. But the Earth's mass is so big that it helps to cancel out some of that times 10 to the negative 11. And if I were to go jump off of a ladder, then I'm going to feel that force of attraction pulling me towards the Earth. Okay, and so that's a quick sample problem on that gravity force. Now, when we look at that, we could say one more thing. So if I look at the equation here, F equals G m over r squared. So if I remember back whenever we did the kickball and the toy car lab, and you stood up on the lab table and you dropped the ball, or maybe you were at home and you dropped an object from your ceiling or from your second story window. I'm going to say when we did that, we could easily find the force of gravity acting on that object by taking that 6.67 times 10 to the negative 11 times the mass of the Earth divided by the radius of the square times whatever the mass of that object is. I'm going to say, you know what? I wasn't really happy with the results of that lab, so we're not going to do a kickball anymore. We're going to drop your desk or a chair. You do it, you do all that calculation again. I say, nah, not really happy with the desk. You know what? We didn't get to do the car mass lab, so I'm going to have you drop your car from the ceiling instead. You do all that calculation. I say, yeah, that was just okay. Instead, I'm going to have you drop your lab partner from the ceiling again. Now, when we look at this equation, in each one of those situations, what stayed constant and what changed? And I would hope that you would say this chunk here, so a little bit of foreshadowing, I kind of wrote it differently. This chunk here stayed constant. The 6.67 times 10 to the negative 11, the mass of the Earth, the radius from here to the center of the Earth squared. What changed was this m value, which was the little m that we had, that we put into that gravitational field. So think through, doesn't this equation, if I lump that together, look very similar to another equation, like maybe Newton's second law, F equals ma? Now, take that one step further and think, if this is the force of gravity acting on the object, what is this acceleration then? Doesn't that acceleration have to be the acceleration of gravity, or roughly 9.8 meters per second squared? So a little bit of coolness there. What we are looking at then is saying, okay, we can chunk this part of the equation together, and we're going to call that a field. It's the area around an object that affects other objects. The field is the area around an object that affects other objects. The field is the area around an object that affects other objects. So when we talk gravitational field, it's the area around a mass that affects other masses. Now, there's nothing at this point in space right here, but if I put my pen here and I let go, I know that it is affected by the Earth, and that's why I would say there's a field, or the gravitational field here, so that when I put something there and let go, it falls because it's affected by that field. Later, we'll talk about the electric field. It's the area around a charge that is affected by other charges. And then we'll talk about a magnetic field. It's the area around a magnet that's affected by other magnets. So the field is the area that affects other objects, okay? What represents that gravitational field around the Earth? We just said it right here. It is the acceleration of gravity. You should star that. You should circle it. You should memorize it. You should file it in the front of your head, because that's on every test from here on out. That you need to know on the final exam what represents the gravitational field around the Earth. It's the acceleration of gravity. So now here is a calculation for it. At crown point, the radius of the Earth is this much, and the mass of the Earth is this much. Calculate the gravitational field at crown point. So if we plug those numbers in, you can't see because of my little facey there. So 6.67 times 10 to the negative 11, plug in that mass, 5.98 times 10 to the 24th, plug in the radius of the Earth, and then square it. Notice that you get a gravity of 9.803 times 10 to the 9.803 meters per second squared. So if you remember back when we studied, we said, hey, this 9.8 is not always constant. And some of you actually may have tried to use 9.81 or 9.79. So think through, if I have the Earth here, I'm standing on Mount Everest, then all the way up I have a larger radius. That value of gravity is going to be smaller, like 9.79. If I go down into the bottom of the Marianas Trench in the middle of the ocean, because that radius is much smaller, I'm going to have a larger value of gravity, and that's where I would get the 9.81. And so we normally just average that out to be 9.8 or 9.81 whenever we are studying those. The last thing that I want to run through is, if you remember in the last chapter, we said, okay, or in the beginning of this chapter, actually, we had a car going around a corner, and we said there's a circular force, mv squared over r, or this is an acceleration, that this is the centripetal force pulling it towards the center. What keeps that on the road? It's got to be the force of friction, and so we can plug in the friction equation for that and plug and chug. Then we had the stopper lab, where we were spinning the stopper. We had a weight hanging on the other end, and we said F equals mv squared over r, and this was the force of gravity of this hanging weight. So it was that mass times gravity, m times v squared over r, and so we could solve for whatever it was we needed to in this case. Now in this one, if you look at the background, we have the Earth and the sun, and we say, okay, so here is the sun, and here is the Earth, and the Earth is rotating around the sun. Then what's pulling the Earth towards the center of this circle to cause this mv squared over r? Isn't that the force of gravity that we just studied? So we can say this equation for the force of gravity is gmm over r squared and equals mv squared over r, mv squared over r, and then we can plug in our numbers and solve for whatever it is. So major ideas. We have this gmm over r squared as our force of gravity. We can lump and pull out part of that to become the gravitational field, which is represented by acceleration of gravity. And then we can also use that force of gravity as something that's pulling an object towards the center of the circle. So email me, text me, Zoom me. If you have questions, I'm here for you.